You good? It's good. You PowerPoint okay?
Yeah.
Okay, great. Thanks.
All right. Well, hi everyone. I'll be discussing ways that we can estimate potential blue carbon benefits in coastal marshes and seaweed. So to start off, many of you might be asking, what is blue carbon? And simply put, it is the carbon captured by the world's ocean and coastal ecosystems. And it's called blue carbon because it's associated with water, not because of the color of the carbon or the water or the plants or anything. So blue is for ocean. And there's a handful of ecosystems that are so far considered blue carbon ecosystems, and they're grouped into these three larger categories based on common pathways for storing carbon and the dynamics around that carbon capture. So these three categories are the nearshore or coastal ecosystems, and these are things like marshes, mangroves, and seaweed. There are, seagrass. And there's seaweed ecosystems, and that includes natural macroalgal systems as well as farm seaweed areas. And then there are open ocean ecosystems, which largely rely on animals to move carbon around. So today I'll be highlighting two examples, starting with the nearshore ecosystem of coastal marshes. And you may be familiar with forests storing carbon in the trees, and in a similar way, nearshore coastal ecosystems sequester a lot of carbon too. And the thing about them is that they can store potentially more carbon in the same unit of area, giving you a lot of bang for your sequestration buck. And in nearshore ecosystems, this carbon builds up in the soils, and they can hold onto it for hundreds or even thousands of years, making them a very good reservoir for storing carbon. However, if these ecosystems are disturbed either by coastal erosion or sea level rise or human activities, then they risk releasing this stored carbon into the atmosphere, and that can make climate change worse. So coastal marshes are very sensitive to the rate of sea level rise. They are adapted to this really narrow band of elevation and salinity right at the margin of the ocean. And in areas that are sometimes submerged by tides, these marshes will grow, and then further upslope, they'll give way to grasslands or forests. And you may have seen that here in coastal California. The marshes then lead into these lovely, rich grasslands. As sea levels rise, the area of optimal elevation and salinity for marshes is going to move landward or up the slope. And if they get submerged too frequently, they're going to lose their vegetation and convert to mudflats. And mudflats aren't bad by any means, but they do have potentially less ability to store carbon because that vegetation is no longer there pulling carbon out of the atmosphere. Marshes can keep pace with sea level rise under some circumstances if that rate of rise is slow enough. And they do this by trapping sediment that is suspended in the water. All that vegetation that sticks up slows down water movement. That sediment falls down to the bottom, and then it eventually forms this very carbon-rich soil. And the buildup of the soil and its elevation is dependent on the amount of plant biomass that's there, how frequently these sites get inundated, and the amount of sediment that's in the water. So 1 centimeter of sea level rise does not necessarily directly lead to 1 centimeter of elevation loss. And it's important to incorporate these processes into elevation change models as we estimate how the distribution of marsh ecosystems is going to change. And so I'm going to share some work that I did while I was at USGS. And we had a study to look at marsh changes. And this study had two objectives. First, it was to look at marsh shifts over 100 years under 5 different sea level rise scenarios and 3 different sediment management scenarios, baseline sediment concentration, and then double or triple sediment concentration as management alternatives. So that plays out to 15 different scenarios. And then we also, in each of these, modeled carbon accumulation in the soil. And so that's where the blue carbon piece of this comes in. And so we did this in the Nisqually River Delta in the south end of Puget Sound. It's in Nisqually, Washington. It's outside of Olympia. It's a very beautiful place. You might have driven by it. I-5 goes right through there if you're heading north towards Seattle. And to do this, we used the Marsh equilibrium model, and it's now available in R. When I was doing this, it was only available via spreadsheet, or this online version that I'm showing here where you can plug and play your numbers and it would spit out some graphs. The spreadsheet version basically did the same thing, only with a few more tweaks and access to more of the numbers. So this model measures elevation change and carbon accumulation of marshes, and it uses input data on elevation, suspended sediment, and plant biomass, among other things. And if you work in tidal marshes, you might be familiar with the SLAM model for sea level rise, and it's basically another flavor of this. This is a point-based model or zero-dimensional, and it basically works on one point at a time. So you may be wondering, if this is a point model, how do you do this in bulk in Excel to process millions of points with all your different input elevations that we got out of this 1 meter LiDAR data set for the entire delta? And there is luckily this free program called BERT, B-E-R-T. It's the basic Excel R toolkit, and you can basically use R to change the values of your Excel spreadsheet and then grab values from the resulting outputs and then spit those into R. And so with that, I was able to take the results out of this spreadsheet for every input round and then generate these elevation change and carbon sequestration rasters for all of our scenarios. And to get data for this model, I used publicly available USGS field data from past studies in the Nisqually River Delta. And this included that high resolution LiDAR map. There was biomass data for the vegetation that came from Quadrat data, and then baseline sediment supply from hydrological models. And all of this data is technically publicly available, but it's not very easily findable. So that goes back to what Michelle was saying earlier. The USGS science-based website has all this information, but you kind of have to know that it already was there to go looking for it. So it's a little bit hard to find, but that's where these meetings come in, where you talk to people and discover data sets. And so to run the model, we used all of this USGS data. And when the model spit out these projections of future elevation, we were able to combine that with a different model for future salinity of the marsh and classify what the future ecosystem type might be. So we had 8 distinct ecosystem types, and those were subtidal mudflat, transitional or low salt marsh. It's going to be in between marsh and mudflat. We had a high salt marsh, brackish marsh, freshwater marsh, tidal forest, and then upland forest. So with that, we were able to map ecosystem shifts over 100 years, and these are projections of that. I'll note that anything that started out as subtidal or mudflat, that the browns and the blues, those didn't get modeled because the model just wasn't designed to handle unvegetated ecosystems. And the starting elevations are down there, or the starting ecosystems are down there in the lower left corner. 2011 was the last year that we had habitat classifications done. So then 100 years later, under these different amounts of sea level rise, we can see what might be there. And over on the left, with just 50 centimeters of sea level rise, you can see there's not a ton of change. There might be a little more transitional salt marsh coming in, but otherwise it's pretty much the same. With 100 centimeters of sea level rise, so in the middle, you see a lot more of that mudflat starting to fill in. And then with 150 centimeters of sea level rise over on the right, you see there's a lot of mudflat forming. The high marsh is basically gone. What's left of it has converted to that lower transitional marsh. So then we can total up all the pixels in these maps and understand how much area is going to be there for each of these ecosystem types under the different sea level rise and sediment scenarios. Now, what does this mean for the blue carbon potential of the Nisqually River Delta? overall less carbon accumulated with more sea level rise. So in these graphs, the year is across the bottom and sediment accumulation is along the vertical axis, and then each of these lines corresponds to a sea level rise scenario, and the darker ones means more sea level rise. And we saw that there's pretty much linear accumulation of carbon when sea level rise is slow, but when it is fast, you start to see this exponential decline in carbon accumulation. That black line just sadly tanks towards the end of the simulation. And this is largely driven by conversion to mudflat, and that's basically has the potential to release a lot of the stored carbon when the vegetation can no longer grow and it's no longer able to trap carbon in the same way. But we see that when sediment doubled, you can better hold on to this carbon, and the total carbon accumulation is actually up to 34,000 tons higher than when in just the baseline levels of sediment. And then when sediment is tripled, the total carbon accumulation is up to 30,000 tons beyond that. And then interesting, we also saw that these lines started to converge, so the amount of sea level rise started to have less of an impact on the total amount of carbon once you got sufficiently high sediment. So these maps and carbon projections will support the Nisqually Indian Tribe and the Billy Frank Jr. Nisqually National Wildlife Refuge staff as they make their climate adaptation plans for the Delta. And this also informs the potential for leveraging the economic value of carbon accumulation to support habitat conservation. So next I'm going to switch gears and talk a little bit more about what I've been doing at Environmental Defense Fund for the last year. And I'm going to talk about seaweed as a blue carbon system. So unlike coastal marshes, seaweeds don't have roots and they don't accumulate soil, and they often live on rocky reefs or they're grown on lines that float in the water. And they offer climate benefits in a slightly different way. So with seaweed, the opportunities for climate benefit involve using that seaweed in ways that reduces our carbon footprint, or you can sink the harvested seaweed directly to the deep ocean where it's supposed to stay for hundreds of years or more. So emerging evidence suggests that using seaweed in products could actually have a greater climate impact by offsetting our use of fossil fuels, and that could exceed the amount of already emitted carbon dioxide that could be withdrawn from the atmosphere and then taken down to the deep by sinking the seaweed. So seaweeds can be used as low carbon inputs in otherwise carbon intensive processes. They can be used as soil amendments in agriculture, and in doing so, they provide micronutrients that can offset the use of fertilizer, which when using conventional fertilizers is very fossil fuel intensive. They can be used as food for humans and displace the consumption of greenhouse gas intensive foods. To give an example, there's a startup in San Francisco trying to make seaweed bacon. And so if you decided to eat seaweed bacon instead of pork bacon for a meal, you'd have a lower carbon footprint for that meal. Seaweed doesn't require fertilizer, land, or fresh water, and so it's a low impact crop comparatively. And it can also be added to animal feed to reduce methane emissions from livestock. And methane is a big contributor to our overall greenhouse gas footprint, and it's particularly potent in its warming effects. And then finally, seaweed can be used in place of petrochemicals for things like bioplastics and building materials and other things in our daily lives. There's also a lot of ecological benefits and social benefits. Seaweed can remove contaminants from the water. They're a habitat and food source for a lot of marine animals. They can reduce the effects of ocean acidification and hypoxia. And then they enhance fisheries and coastal livelihoods, such as our kelp forests acting out here. So with my remaining time, I'm going to focus in on seaweed blue carbon, and specifically farming seaweed. And we want to know, where can we scale up seaweed farming to produce the most climate benefits? We also want to know where we can realize other ecological and social benefits in doing so. So sadly, I did not get to handle any seaweed as part of this study. All I needed for this was a laptop, GIS software, and an internet connection, which has its benefits, but it would also have been nice to get to work with some seaweed directly. So we used public data from the MacMods model, which details where seaweed can grow under proper light, nutrient, temperature, and wave conditions. And then from these efforts, which are published now by a group at UC Irvine, we know that seaweed can grow in large swaths of the ocean. So all of this bright yellow area are places that have good conditions for seaweed farming. But as you can see, it's a really large area. That's a lot of the Pacific Ocean and areas not shown on this map as well. So there's a lot of options. And so we asked, where can we farm seaweed and get other benefits from that as well? And there's a lot of choices as to what society wants from this. And so we built a spatial model that explores some of those choices. And in addition to MacMod's data on seaweed harvest and the cost of producing that seaweed, we incorporate a lot of other data sources, and this included the ecological benefits and things like ocean acidification and dissolved oxygen. There are data sets for that available through BioOracle at global scales. So I did all of this at a 1/12 degree resolution, more or less, which is pretty coarse for regional planning, but for global scale, it works just fine. And then I also wondered, where can seaweed pull nutrients out of the water? And conveniently, Esri makes this eutrophication index layer that tells you where are their eutrophication index or events, where have they happened in the past? And that gives you some sense of where there might be excess nutrients that you might want to pull out of the water. I also looked at where farming seaweed might cause conflicts and problems. So you wouldn't want to farm seaweed in the middle of a shipping lane or potentially a popular fishing ground. And so the Ocean Health Index publishes these aggregated data sets on where these activities are taking place. They pull it all from AIS data, those transponders that go on large boats and ships. And then they nicely scale it into in this index of where the most effort is happening. We also didn't want to say, go ahead and farm seaweed on these sensitive coral reefs. And so there's a lot of data out there on sensitive habitats published by the UN Environmental Program, and we got a coral reefs layer from them. Lastly, since seaweed farming is a long-term endeavor, we wanted to know where are the areas going to be suitable temperature-wise for farming seaweed into the future. And so we looked ahead 30 years to the 2050s, looking at what are sea surface temperatures going to be then, and you can get climate projections from the CMIP effort, the Climate Model Intercomparison Project. So I combined all of these data into this large GIS model, and it turned it into scores for each of these categories, ranging from 0 to 1, 1 being sort of the most desirable state for that variable with regard to seaweed farming and with regard to environmental benefits or social benefits, and then 0 being the worst. And I divvied all these up by the exclusive economic zones for each country to keep it a little more relative. And so this is what these scores look like when mapped out for every pixel. I basically took all the variables in each category and averaged those scaled scores, and we get these these basically average scores for the category. And the cool shades indicate more favorable conditions for seaweed farming, while the warm shades indicate less favorable conditions. So if you're a planner and you're trying to guide development of your country's seaweed farming industry, you might want to prioritize placing farms in areas where seaweed can reduce stressful conditions. And that will give you a very different answer as to where you might want to do that than, say, if you're prioritizing just avoiding conflicting marine uses. And so You can see in these maps, if you're trying to improve environmental stress, there's not as many places where you get a lot of opportunities to do that versus avoiding conflict. You have a lot more options. There's a lot of dark blue on these maps. Pretty much just stay outside the major shipping areas, and you'll do fairly well. So we weighted these in 4 different ways because planners care about different things. We basically create a weighted average and rotated around the category that got the most average. So any one category would get 40% of the weight, and then the rest would get 20%. Now, if you're a planner and you have stakeholders who if you're a planner, you probably have stakeholders that collectively care about all of these different things. So where are you going to make the most people happy, or at least the least upset by prioritizing seaweed farming in those areas? And what's the most important factor to you then? Depending on what factor you prioritize, between 0.8 and 9.9 million square kilometers of ocean would have highly favorable conditions for seaweed farming. And here, highly favorable means that they scored 80% or higher, or 0.8 in our weighted average. And this graph shows that area. So prioritizing future temperature is going to get you almost 10 million square kilometers of nice seaweed farming area, whereas prioritizing improvement of stress is going to get you less than 1 million. So instead of looking at only one of these categories to prioritize, we can look at all of them to see which areas are going to score well, no matter what. So we counted up how many of these different scenarios had high scores or met that 80% threshold for every pixel, and then we mapped it out. And so these darker blues indicate more scenarios that met that threshold, more scenarios with favorable conditions for seaweed farming. And we found these clusters emerging where there's favorable conditions, despite or no matter what you weighted the most heavily. And so these things included the Gulf of Alaska and British Columbia, the Galapagos, Argentina, a little bit of offshore Hawaii and New Zealand, and then a few areas in the Southern Ocean. And so these maps can be continually refined as new data becomes available, or we can sub in more locally relevant layers depending on what scale we're working on. Just to give an example, we want to do this for the Philippines, where we have a demonstration seaweed farm. And we want maps like this to serve as a guide for the rapidly growing seaweed industry and the stakeholders that surround it. So there are these geographically widespread trade-offs in the benefits that you're going to get from seaweed farming. And so to address this, stakeholder priorities need to be considered in guiding where the seaweed industry can invest, selecting regions to model at a finer scale, and then informing larger government policies on where to incentivize seaweed farming. And even with all of this, complicated trade-offs, it's encouraging that there are several regions around the globe that offer these multiple ecological and social benefits, while still potentially offering robust harvests and potential carbon offsets now and in the coming decades. So with that, I wanted to acknowledge the Nisqually National Wildlife Refuge and the Nisqually tribe for helping steer the Marsh research and providing data. And then I also have to thank my collaborators at UC Irvine for the Seaweed Project. So thank you for listening. If you're interested in learning more about blue carbon, we've got these reports out, and then I have a QR code that goes to the Marsh modeling study up in the corner. And thank you for listening.
For a question.
So I don't know about seaweed farming, so this might be a question, but did you ever take into account the, I guess, the cost of farming seaweed into your model? So like constrained by the EEZ, but is it really realistic that they would actually be farming seaweed 200 nautical miles offshore? And did you factor in, like, or prioritize areas that would actually be accessible to farming?
Yeah, so the question is, did we factor in costs of seaweed farming? Because it might not be realistic to farm it really far out in the ocean. And so the MacMod's model data actually has a layer for the cost of farming, and that includes things like labor and transport, fuel costs and equipment. So all of those things go in, and then I gave that kind of equal consideration with the amount of seaweed actually farmed.
I'm wondering if it would be possible to validate your sea level rise model and estuaries using sub-bottom data to see how the sediment accumulation affected over the past several thousand years or so.
Yeah, so the question is, could you validate the Marsh sea level rise projections using sediment and sub-bottom data? And so we parameterized the model using soil cores that came from those marshes. And then, so they just took new LiDAR data in 2021, and in 2022 they were processing it. So like now, I think you could compare the 2011 and 2021 LiDAR data to at least see how the first 10 years of the model performed. And they also have sediment elevation tables. Basically, they're these like rods that are suspended above the soil, and then you can get really precise elevation measurements over time. And so they're tracking the marsh surface as it moves over time that way. So you could then compare the results, like how much elevation did you gain or lose? And then what does the marsh look like in 20 or 30 years, and how well does it line up with the maps?
Have you tried the seaweed-based bacon?
I have not. They last I heard they're still in prototyping phase. And they went on Shark Tank and offered it to them, but they have not offered it to the general public yet.
Did they get funded in Shark Tank? Do you know?
I don't think they did. I guess it passed the sandwich test, but it didn't pass the breakfast test.
Oh, interesting. Breakfast for you. It's intriguing.
Yeah.
I have a quick question. For your seaweed modeling, I was curious about the temperature suitability, because I would think that different species might actually benefit from higher temperatures, and it seems to be very species dependent. So I was just curious how you aggregated all that information to seaweed in general.
Yeah, that's a great question. So the question was, how did we deal with the temperature data and species specific temperature tolerances? So the way that the seaweed growth data worked is it binned things into tropical and temperate species, but they had pretty wide suitable temperature ranges. And so for things that like stayed within, or basically anything that stayed within those present day temperature bands got a really high score. If you were in the middle, like depending on how far away from those optimal bands you were, it got an intermediate score. If you're outside of either physiological limit, either too hot or too cold, it basically knocked it out. But you could, in theory, move out of your temperate temperature range and have a period where the temperature is so, and then move back into a really good temperature range if you get warm enough to enter that tropical band. So I guess if you were to graph it out, there'd be a really high scoring, you'd get a little dip in the middle and come back into high scoring area.
Right.
All right.
Thank you.